Next, take a look at something a little more complicated. Again, this is going to be at rest. And so we have a situation where you have a string pulling this way and another string pulling this way. And I hang a mass on this third piece here. Now, we can pretty much see, if I could call this FT3, but we know FT3 is equal to mg, because if I look at the free body diagram of just this part here, I have tension pulling upwards, we call it FT3, and this mg. So these are basically, you could treat it, the mass, as if it was sitting right here if you wanted to. Just to make it look nice, I kind of put it there, but we can call this vector, or the force acting downwards, as just mg and kind of ignore the FT3 altogether, because it would amount to the same thing. Now, if I wanted to find what are the tensions of FT1 and FT2, what are the tensions in these two strings, I can again use Newton's second law. I know that the sum of the forces in the x direction is 0, because this thing is not moving. And the sum of the forces in the y direction is 0, again, because this is not moving. So what I would do in this case is make my free body diagram. My free body diagram looks like this: FT1, FT2, FT1, and mg. And this is static, meaning the sum of these forces is going to add up to 0. And so we can individually separate out the x and y axis and know that the sum of the forces in the x direction have to be independently 0, and the sum of the forces in the y direction have to independently be 0, since there's neither acceleration in either direction. So then I'll look at these forces. This force has two components. If I were to redraw it again here, that's FT1, and it has two components. I have FT1 in the y direction and FT1 in the x direction. And then I have mg here acting only in the y direction. So the forces in the x direction have to cancel out the forces in the y direction. The sum of the forces in the x direction, this is negative, so that'd be negative FT1. And then this component would just be the sine of the angle, because I'm looking at, these are the two components, one pulling this way, one pulling that way. And so this one would be the sine, because it's the opposite. And so FT1 sine of theta, which is this component right there, has to equal to the FT2, which I didn't draw yet. So again, this is my one force, this is my second force, that is my third force, and I have broken the third force, or this one, FT1, into two components, FT1x and FT1y. So if I look at just the components in the x direction, I have this one here that's right there, and then FT2 pulling to the right, which is positive there, and these have to equal 0. So then I have an expression here that says FT2 is equal to FT1 sine of theta. And now I look at the forces in the y direction. And so this has a component in the y as well. FT2 has nothing to do with the y. So FT1 cosine of theta must equal to mg. Now I have two equations and two unknowns. And so I could easily substitute one to find the other. I would say that ft1 is equal to mg over cosine of theta. I could plug that in here, and then I would say ft2 is equal to ft1, which is mg over cosine theta. So I replace the ft1 with this thing here times sine of theta. So then I can calculate my ft2, which would just be mg times tangent of theta. Once I figure out ft2, then I can just plug it back in here to figure out ft1. So then ft1 would equal to ft2 divided by sine of theta. So now it's just a matter of plugging in numbers. If m was, say, 3 kg and g, of course, is 9.8 and tangent can be whatever angle, we could solve for ft2 and then ft1 using this. Oops, sorry. So you could use this to figure this out as well. And so that's how you would work on any problem like this. They can get more complicated. You might have something that looks like this, for example. And so that's theta 1 and theta 2 and ft1 and ft2 and then mg acting downwards. And you could similarly work through a process like this to resolve the ft1 and ft2. Again, you would end up with two equations and two unknowns. We would have, instead of this one here having only one component, now it has two. So we would basically solve something by setting up the equations to say that the force is in the x direction, which is ft2 cosine of theta, that's in the x direction, plus ft1 cosine of theta 1, that's theta 2, is equal to 0. The sum of these two forces, where of course you could write this one as being in the negative direction and that one being in the positive direction. So that'd be a one equation. And then in the y direction, you would have ft2 sine of theta 2 plus ft1 sine of theta 1 plus mg, or let's say that minus mg, because that's downwards, is equal to 0. And then using the two equations and two unknowns, just by using substitution like we did over here, you could resolve something like that as well. Okay, so that is how you could work and figure out the tensions when you have them at an angle. Again, we are utilizing Newton's second law in each case. Sum of the forces equals ma, and it just so happens that our a is 0, so our sum of the forces is always going to equal to 0, like it does here.